With single channel signal enhancement, we talked about the model. We worked about different filtering methods in the time domain. Then we moved to the we continue with the frequency domain. GIAN, which is also filtered. And then we presented three methods like this, the Wiener, which are just examples. Of course, you can work with other examples, the Wiener, the trade-off. We saw also that we can also use a parametric Wiener gain. We talked about these theta and so on. So these are just examples, and to get understanding and also the equivalence or comparison between time domain filtering and frequency domain filtering. But in practice, of course, we don't work on long signals. We work in the short time Fourier transform domain. So the extension is we have different methods or different ways to move from the frequency domain to the STFT domain. The simplest method is to work with similar gains that we worked in the frequency domain, but apply them in the short time Fourier transform domain. What does it mean? That we take long signal, we use windows, and the length of the windows, we need to choose it in a good way. So it's not too short, it's not too long. Sometimes it's possible to combine different windows and make the enhancement using multiple windows. Sometimes it's possible to choose long windows for low frequencies to get higher resolution in the low frequency, and short windows in the high frequencies, because high frequencies we need less frequency resolution, we need more time resolution because they change more quickly than low frequencies. So that also makes sense, so we can combine. But here, just to give you intuition and understanding, we will work with constant length windows for the short time Fourier transform domain. Okay? So what we do here, we start with a time domain signal. You see these are the vectors, just like we did in the time domain. And we take a length, a certain length. Suppose that we use a length of L of the signal. So we took L samples of the measurements. And then using DFT, discrete Fourier transform, and there are fast algorithms to do that, we move to the Fourier transform. So we can apply DFT to each windowed measurement, or window of length L. How do we do that? We have to use windows. If we don't use windows as just rectangular windows, there are some problems and some artifacts. So it's not good to use rectangular windows. Also, when you use the short time Fourier transform, it's important that the analysis window and the synthesis window, which means for the forward short time Fourier transform and the inverse short time Fourier transform, they satisfy some relations. And these relations enable perfect reconstruction of signals. So if you don't process anything, you just do short time Fourier transform and then the inverse transform, you want to get the same signal, just like you start with. So this is called perfect reconstruction. And this we can formulate mathematically this requirement by a certain relations between the analysis window and the synthesis window, as we will see shortly. Okay, so how do we do it? Suppose that we choose here an analysis window of length L. Analysis window, common analysis window, Hamming window, and similar windows. So you have selections of windows. And then once you use analysis window, you will have to choose also a window for the inverse short time Fourier transform. based on this window. Okay? And we will discuss how to compute the synthesis window. Here, this is the matrix of the discrete Fourier transform, which we know. So what we do here, we take the vector of measurements of length L. We multiply each sample in this vector L with the sample of the window. Okay? So we can write it as diagonal matrix of G that is multiplied with Y. Okay? So we have here only L multiplications. This is the windowed measurement of length L. And then we'll multiply it with the matrix of the discrete Fourier transform, this matrix, which is L by L. And we get a vector of length L that contains the frequency bins for this time window. And then we can move this window of Y. How much do we change? How much we need to move? How much? Maybe half. Yes, so it should be less than L. So the jumps that we use for the window, so if we use a window of measurements of L samples, then we will move to the next window. Generally, we can move by one sample, or we can move by more, but it should be less than L. Okay? The question is why? I will ask you, think about it, and I will answer it soon. And what is the effect of the overlap? Why do we need overlap? This is also a question that think about it. Why do we need overlap between the windows of the short-time Fourier transform? Anyway, in practice, you don't multiply with this matrix, of course. Okay? Because if you just multiply, the number of multiplication is large. There are fast Fourier transform algorithms that equivalent to multiplying with the matrix W because of this structure of W. So you don't directly multiply it with this matrix. There are algorithms to do it. Instead of L squared, order of L squared computations, you do it L log 2L computations. So they are more efficient. Okay? We know how to multiply efficiently with the matrix W. And this is a vector that contains the frequencies. So the length of this vector is L, which contains the frequency. And we do it here. What is the index T? Generally, index T here, it doesn't have to be the time. It can be the index of the window. So if we jump with windows, this will be the index of the window. Okay? I will write it more specifically in a minute. Okay? So instead of using here T, so we can have an index R for the window, and this is the jump, how much we jump, how many samples we jump from window to the next window. Okay? So if we have a signal, yt, okay, so this is t, time axis. So this is the window, and then let's say that we jump R samples. And the index, so the index of the window will be R, okay? So we can say, okay, it doesn't have to be causal now, even though that we mark it here, but the index here will be R equals to 1, okay? So it will be R equals to 1. Here, for this window, R will be equals to 2, and so on. So what we get, if we started with samples of yt, we have samples like this, samples okay, as a function of t. Okay, t equals to 1 and so on, 2, 3, and so on. For the short-time Fourier transform, we have it as a function of r, and it can be k, for example, if you like. So it will go like that. It will go as a function of r. Maybe I will multiply it so you see the equivalence in the time. But this r is constant. It's just the jump that we do. This is k. So k goes from either, let's say, from 0, 1, 2, and so on, until L minus 1. And R is 0, 1, 2, and so on, whatever you like. So if we jump, it will be like this. So this is 0, this is R, 2R, 3R, and so on. 4R. And for each point on the grid, so you have a measurement. It's like samples, like here. Okay, so you have a grid like this. Okay, all this grid, and so on. So you have a grid, but for each window, it's a vector. Okay, this is the short-time Fourier transform, and of course, the values are complex numbers. So we see it like here, in a block form. So if we have a vector of x, of length L, a vector of noise of length L, we have the summation. Then we multiply with the window. Multiplication with the window is similar to multiplication with the diagonal matrix. That the diagonal are the window values, the window samples, coefficients. Then we do the Fourier transform for that windowed vector. And we get the frequencies for the window for t, and then we downsample. So actually, we don't compute it for every t. We just compute it for indices r. So the jumps. Okay, and as I said, that r can be 1, which is okay. And it has to be smaller than L. And if we choose a certain window G, for the analysis, for the short-time Fourier transform, we will need to compute synthesis window, which we will talk about the inverse short-time Fourier transform. And the synthesis window depends on G and R and L, actually. Okay, so all these parameters determine the synthesis window. But once we do it, once we work in the Fourier transform, in the short-term Fourier transform STFT domain, we can write this as the summation, okay? Because we have linear relations of the STFT. So we have for each sample, each measurement, each sample here, complex number, it's summation of the complex number of the STFT of the clean signal and the STFT of the noise. And then we can compute the variance of the measurement. It contains the variance of X and the variance of V. So you see the equivalence between Fourier transform domain and the STFT domain. So what we can do is to apply a gain, scalar complex gain, to each pixel here, to each value here. Okay, so this is the model in the STFT domain, and we apply a scalar complex gain to each measurement here, noisy measurement here. And we apply the gain. So if the signals, the desired signal and the noise signal are stationary, so this gain, it doesn't need to depend on R. Okay? So it doesn't depend on the time axis. It depends only on the frequency. So here the gain can depend only on K if the signals are stationary. But generally, signals are not stationary. So the gain should be computed or adjusted also in time. So it depends on the time index, R, and the frequency index, K. Okay? And after we find this estimate of the clean signal for each time frequency bin, we need to do the inverse STFT. How do we do the inverse STFT on this? Okay? But before we continue, think about in time. So when you work in time, you work with the filters. So it can be causal filters. In the STFT, there is some latency. So even when we work on window, okay, so in order to process this window, we need this window, and so on, and then this window, and so on. When we do the inverse, there is overlap. So there is some latency between the output and the input, which you need to take that into account. Okay? So when you think about real-time processing, you need to think about how much latency do you have, even if the processing is immediate or it takes time. So, but this is acceptable. So there is some relation between the latency, the output from the input, and which depends on L and R. So sometimes if you want to reduce the latency, you need to use shorter windows, and also it depends on R. Okay, so you need to take that into account. Now, if we write the time frequency bin of the estimate of the signal and the gain, so these gains, very similar what we did in the Fourier transform domain, we can take the same gains. The problem is that the information that is used, so sometimes in the frequency domain we can get the information. In the STFT domain, for non-stationary signals, it's quite challenging, as we will see even with the Wiener filter. Okay? But the expressions for the gain will be similar. So whatever we used in the frequency domain and more, even more expressions, more criteria or other filters, we can use in the STFT domain. I will give you an example, a practical example of speech enhancement, non-stationary signal, and then you will see the challenges of working in the STFT domain with non-stationary signals. How do we do the inverse Fourier transform? Okay, so it looks like that. We take this vector. Suppose that we have this matrix in the time frequency domain for the enhanced signal, for Z. Okay? So we take each vector here, each vector. We apply the inverse Fourier transform for this vector. You see? You take this vector, you apply the inverse Fourier transform, which is like multiplication with the W conjugate transpose. Okay, this is the inverse Fourier transform matrix. And of course, I remind you, we don't actually multiply with this matrix. We have fast algorithms to do that for the inverse Fourier transform. So we apply the inverse Fourier transform, and then again, we multiply with a certain window. The window is G tilde. So this is the synthesis window, G tilde, of length L. And then we get samples of Z, okay? See, this is capital Z, which is in the time frequency domain. This is small z. This is a vector of time samples of the vector Z. We get a vector here, and a vector here, and a vector here. And then we do overlap and add. Okay? So what we do, we take ZT, the samples of Z, are overlaps. And this is an indicator just to show what we do with the vector here. So actually what we did, we take vector of signals, and then vector of signals. We move it by our samples, and then we move it. We move it again with our samples and so on. And then each sample, T, is obtained by summation of these windowed vectors. Okay? So there is relation between G tilde and G. This is the analysis window, and this is the synthesis window. Okay? Here, like this. So this is the synthesis window. This is how it looks. Block diagram of the inverse STFT. We multiply with the inverse Fourier transform. We multiply with the window, overlap, add. Sometimes people who are not familiar with STFT, they choose analysis window. They don't do window, which is equivalent as if we choose G like this. So sometimes people who are not familiar with STFT, they just take samples from 0 to L minus 1, so they take rectangular window, which is equivalent. So they don't multiply with any window. And also in the inverse Fourier, inverse STFT, they take the same G tilde, like this, rectangular window. Actually, this is not perfect reconstruction. It creates some problems, so on. So this is not a good choice. And in addition, that the inverse Fourier STFT does not reconstruct the original signal, it creates also artifacts. So let's talk about the relations between the analysis and synthesis window. If we take, you see, suppose that we take any signal like this. We multiply it with a window and apply the Fourier transform. So this is the STFT of the signal. Now suppose that we want to reconstruct the original time domain signal from the STFT signal. So we apply the inverse DFT, we multiply with synthesis window, and this is the overlap and add. Okay, we take the signals, we move it by our samples, and this is the overlap and add. So we can write the relation between the time domain signal here and the time domain blocks, vectors of length L, like this. So in order to have this equation correct for any signal X, this is called the perfect reconstruction condition. So if we want to have perfect reconstruction, we need that this will be satisfied for any time signal X. which means that this, you see here, so this relation should be satisfied. From here, we can come here. By the way, anybody that wants to go through the mathematics, just do it and prove any step in the derivation. But I want you to understand it, so I don't go about all details, but it's straightforward if you do it yourself. Okay? So this is, if we require that this is satisfied for any time signals x, so this should be satisfied. This is called the exact reconstruction condition. So you see, it depends on what we chose for the analysis window, the G, what is L, and L, because L comes from here, the G. The window G, its length is L. Okay? And then we have here another parameter R is how much we jump or we move from one window to the next window. So all this determine what will be the synthesis window. So what I say that you here, suppose that you choose an analysis window of length L, and you choose step size R, then the solution to that, there are infinite number of solutions to find G tilde synthesis windows that satisfy the exact reconstruction condition. So there are many solutions. But usually we choose the solution with the minimum norm. Okay? But you need to know that this is just one solution out of infinite number of solutions so that you can choose, but it makes sense to choose minimum norm because it's a smooth with and a minimum norm, which means that you don't have much variation in the synthesis signal. Okay, so how do we find G tilde from this equation, the minimum norm solution? We can write it in a vector form like this. Okay, we can write it like this. This is the condition, the perfect reconstruction condition like here. And minimum norm solution for that, it's simply like this. This is the minimum form solution to this vector form perfect reconstruction condition. So the minimum norm solution, like here, is simply, we can write it like this, sample by sample. Okay, so it means that if we choose a Hamming window, many times people don't choose rectangular windows from the analysis and synthesis because they understand that it's not perfect reconstruction. But what they do, they choose the same window, like, for example, Hamming window for the analysis and synthesis. This is also incorrect. Okay? Because you need to choose a window, synthesis window, that satisfies this condition. By the way, if two windows satisfy the perfect reconstruction condition, they are called biorthogonal windows. Okay, let's move on. Okay, so the input SNR for each sample is this ratio, is the variance of X in that sample divided by the variance of the noise in that sample. And then we can get optimal gain just like we saw for the Fourier transform. We can apply that. We can also compute the wideband input SNR and wideband output SNR like this, which is summation over the time and frequency indices, all the time frequency bins that we want to apply and measure that. And we can also compute the broadband noise reduction factor and broadband desired signal reduction factor. We just take the summation instead of what we did for the Fourier transform. We took summation only for the frequency, or we wrote it as integral, but it actually can be thought as summation. Here we take summation over the time indices of the windows and also the frequency indices. So we take summation over the time frequency bins of the STFT. We can also compute the broadband MSE as summation over the time and frequency of the MSE for each time frequency bin. Let's see an example. Okay? So in this example, we would like to work with a practical signal, like a speech signal, that is sampled at 16 kilohertz. Okay? Afterwards, I want you to repeat this example and do it on your own voice. Okay? And play with this, because this is a very nice example to work with and try it on your own. Okay? So suppose that I have a speech signal and it's contaminated with Watt Gaussian noise with a certain variance. Okay? So the input SNR, and suppose that we work, we apply the STFT, short time Fourier transform, with a certain, with Hamming windows of length 512 samples. 512 samples for 16 kilohertz, it means like the length is 32 milliseconds. 32 milliseconds makes sense for speech because it's not too short interval or window and not too long. So we can assume that within this short window of 32 milliseconds, the signal X is almost stationary, which is not completely true, of course, but it can be approximated as stationary within that window. So if we want to apply the Wiener filter, so the Wiener filter will generate, okay, some distortion. So of course, if the noise is large, if the input SNR is low, we need to reduce more noise, and then what will happen that the distortion, the signal, the enhanced signal will sound more distorted compared to the original signal. But see what happens here. Okay, so this is the Wiener, which is, we know, just like in the frequency domain, we derived it, so we take the same expression. So the input SNR divided by 1 plus input SNR for each time frequency bin. And I mentioned here that the input SNR, it's very difficult to know for non-stationary signals. Okay? So first, what you can do at home, you can take the code and try to put input SNR for time frequency bin R and K. If I take something like instantaneous input SNR, suppose that I take in the STFT domain X, RK, R. RK. So I take the time frequency domain of the clean signal, and I take its magnitude squared without expectation, because I don't have it. It's a realization of the signal. And I take here V, R, K. Okay, something like that, magnitude squared. Suppose that this is like instantaneous input SNR for a specific time frequency bin in the STFT domain. This is like ideal something, suppose that I knew to obtain this ratio, and I put it in the expression of the Wiener filter, it will generate excellent performance. What do you think? Even if I take something like that, the enhanced signal will be distorted compared to the original signal or not? Will I get some distortion or not? Yes or no? 50%, you are right. Even without, just say, if you don't say anything, it's incorrect. But if you try yes or no, then you have 50% correction. 50% correct. So it's better to say something, okay? It's better to say a wrong answer because with 50% success than not do anything. Okay, so if you want to start your own company, so you can say, I will not be able to do that, and I promise you, if you don't do that, you fail. But if you do that, you have a certain percentage or certain probability to succeed. So it's better to try. And if you fail, you try again. If you fail, you try again, okay? So don't be afraid to try. It's not a problem to fail. And it's not a problem to say something which is wrong because it makes you progress, okay? So what do you think? If I use this ideal input SNR, I use it for the Wiener gain, and I apply it to the original signal. Will the enhanced signal will be distorted or not? Yes or no? Yes, of course. It will distort because Wiener filter distorted. If I want that the enhanced signal will not be distorted at all, what do I do? What? Again, it's hard to hear if you speak louder. What? Yeah, but I don't want you to say just NVIDIA. I want you to say, because it's a simple, much simpler answer you can give me. Okay? Think about, suppose that I know which samples here, which time frequency beams contain desired signal and which do not contain signal. So I will use a different gain, H. How will it look like? So it can be 1 if X, R, K, okay, is not 0. 0 if X, R, K equals to 0. Do you agree that I can choose a gain like this? So if I multiply Y, each sample of Y, each time frequency beam of Y, I multiply with this gain. And then I do the inverse, STFT. Do I get any distortion of the signal? Of the desired signal? X will be distorted in the output? Yes or no? I hear yes or no? No distortion. Right? No distortion. Because I didn't touch, I didn't change any sample, any time frequency beam that contains the desired signal. No distortion. But think about, by the way, this kind of method, it's called mask. Why? Because it's mask. It's just, I multiply each beam with a mask. So I estimate where the desired signal is present, where is not. And then I have no distortion. Do I get perfect noise reduction? Yes? Perfect noise reduction? let's remind you that we have trade-off between signal distortion and noise reduction. So do you think that Z which is actually H, mask. This is, sometimes we call it a mask. If we multiply it with Y, and then we do the inverse STFT, do you think we will perfectly reconstruct the original signal without any noise? No. Why not? Why not? Okay, so there is still noise. So we keep the noise in all time frequency bands where the signal is present. But we put to zero all the noise components which are only noise. So remember, we talked about signal plus noise subspace and noise subspace. So noise subspace in this representation is all the time frequency bands that contain only noise. So we'll null them. We put them to zero. And all the time frequency bands that contain signal plus noise, we keep them without touching them. So we keep the noise in those time frequency bands. Okay? So I want you to try this with a Wiener. I want you to try this perfect mask. Okay, so this is a perfect mask. But actually, and then you can compare. Okay? When you compare, try to listen to the enhanced signal. Try to listen if it's distorted or not. And don't compare for high SNR. If the SNR is high, then H becomes closer to 1. Okay, so try to compare when the signal-to-noise ratio is low, 0 dB. Even lower. Try even lower, minus 5 dB. It's nice, okay? But think about this mask is like ideal mask because it shows like I know the clean signal. By the way, this mask is even not something that we try to achieve, okay? Because if there is a very, very small contribution, very small value here, we don't want to keep it. Okay, so usually it's not based on X. It's based on how much X is larger than V by a certain threshold. So this is another way for ideal mask to put it like this. So it's either 1 or 0. By the way, it doesn't have to be binary. We can take something like Wiener. But also, you know, I will put even something like the Wiener, okay? So I will use this input. Input SNR divided by 1 plus input SNR. Okay. For each time from here, we can use it here. If input SNR is larger than a certain threshold, which is epsilon. And 0 if input SNR, the instantaneous, this is the ideal, is smaller than epsilon. And you can choose epsilon according to what? If I increase epsilon, what happens? If I increase epsilon, do I increase distortion or reduce distortion? Increase? Decrease distortion? Actually increase distortion. Let's think why. If I increase epsilon, it means that I keep or process, or here, I keep time frequency beams such that the value of x is sufficiently high. Here I can put some value. Here I put to null all time frequency beams such that the instantaneous SNR is lower than a certain threshold. It means that I will distort very low, very weak components of X. Weak components compared to the noise. Okay? So if I put to 0, I remove weak components of the original signal, I have some distortion. But the distortion will be low. It will be low because I remove only weak components, not the strong components. If I take epsilon larger and larger, I will reduce more noise, but I will pay for that. The distortion will be higher if epsilon is higher. So you can try this kind of Wiener, ideal Wiener, combined with a mask, with ideal mask. Okay? Why do I call it ideal? Because I assume I have the instantaneous SNR for non-stationary signal. So this is very difficult to achieve, this ratio. But we try to approximate, to find it differently. Okay? So let's continue. Any questions so far? Any questions? Okay, good. Actually, it's good if you have questions. If you have no questions, I don't know if everything is clear or not. Okay. Okay. So if you have questions, please ask. Now, okay. In practice, of course, we don't know the input SNR. In practice, we don't know this ratio. This is. I will give you the MATLAB code to do speech enhancement, and then try different things. Play with it. So this is a very good assignment. Even though I don't write it, I didn't put it on as an assignment. I think it will enable you to understand the challenges in practice for real signals and non-stationary signals. So I encourage you to do that. It's very important. Now, because I don't know that input SNR, what can I do? I will try to estimate the variance of V. Okay? So the variance of V, I will take it during windows that don't contain the original signal. So for speech, you see when people speak, there are always some pauses of speech, either in the time or in the time frequency beam. So sometimes I know when speech is active, during which windows there is speech or not. There is something like that. These are algorithms. Do you know how we call these algorithms? What? Voice activity. Exactly. Voice activity detection. In short, VAD. Voice activity detection. There are efficient algorithms for voice activity detection, which are very important. And actually, it enables us to do some things, you see. So if we average the measurements, the noisy measurement in the STFT domain, recursive averaging, which is very efficient to do, we can obtain the variance of V, because during these windows, we don't have the desired signal. We assume the desired signal is 0, or in practice, it's below a certain threshold. It's weak enough. And if there is a present desired signal present in the window, we don't change the variance. So we stop the recursive averaging. This is a good way to estimate the variance of the noise. I remind you that input SNR, what is the input SNR? Instantaneous input SNR. In practice, let's delete this. So I remind you that, that in practice, the input SNR is phi x divided by phi v. So we can put here estimates. So phi v, if the noise is stationary, this is a good way to estimate the noise. If you're interested how to estimate non-stationary noise, I can give you a nice paper about it. If you're interested to know more, I can give you, you can read a paper. It's not complicated. But I don't want to go beyond too much outside the scope of this course. Okay, so if the noise is stationary or changing slowly, not too fast, then this is a good way, recursive averaging during inactivity of the speech. It's a nice way to estimate the variance of the noise, the denominator. The main problem with speech is to estimate the numerator, the variance of the desired signal, because it changes very quickly. Okay, so how do we do that? So a simple way to do that is to take the variance of y and to remove or subtract the variance of v. Okay, I remind you that the variance of y equals to the variance of x plus variance of v. Because y, this is in the STFT domain, equals to x plus v, and x and v do not correlate with each other, aren't correlated. So this implies this. But this is true for the true variance, not for their estimates. That's why if we try to estimate phi x hat using phi y hat, an estimate of variance of y minus variance of v, we cannot do that because maybe it's negative. These are estimates, so it's not satisfied for the estimate. So we put here max between this and 0 because we want it to be larger than 0. And actually, for speech, we can put here a factor, beta, where beta is larger than 1. And the effect of beta, what will happen if we increase beta? It means that we put, remember mu for the trade-off? Remember mu? Good. So if this is similar to mu. So we put more weight to the variance of the noise. So it's just like if I put mu, if I put here a square root of mu, you remember that this is similar to the trade-off, okay? But instead of square root, I call it beta. So but it's the same role, the same feature, like to put here square root of mu. And if I increase beta, okay, what will happen? I give more weight to the noise. It's just like I increase the subtraction of the noise. And then what will happen? If I use larger beta, what will happen? I reduce more noise or less noise? More noise. Very good. if I increase beta and subtract more noise, what will happen with the desired signal? More distorted. This is the trade-off. So I can use something like that here, and I can change beta. Increase beta, more noise reduction, more distortion. Let's see. This is clean signal. This is the spectrogram. If you're not familiar with spectrogram, actually it's the magnitude squared of the STFT. So we call it, just like the matrix I showed before, it looks like that. So first, take a speech signal. You can record yourself using the laptop. You can speak, recording, and then compute the magnitude squared of the STFT on a log scale. So this is in dB. The color or the shade goes like it's after we convert it to dB in decibel. Okay. You have the code, MATLAB code, because this figure comes from the book also. So you have the MATLAB code. You can play with it. This is the clean signal. You see, no noise. Very clean. This is the clean signal in the time domain. By the way, sometimes if you want to put a figure of speech in a paper that you write, conference paper or journal paper, this is a nice way to achieve it. So you can use my code to generate something like that, okay, to see how much noise and so on. So it's a nice way. And you can do it also with color, if you like. Also the spectrogram. Here we see the gain in SNR, the MSC, the noise reduction factor, and the desired signal reduction factor. For a noisy signal, let's see what is the noisy signal. How much noise? I added some noise. Okay. Maybe I have it here. So I have some noise. Oh, okay. So it's as a function of the input SNR. So I can take the clean signal. I can add Y stationary noise such that the input SNR will be certain value. This is the broadband input SNR. Okay, so the blue line is with beta equals to 1. This is red, beta equals to 2. And then 3 and 4. So you see for a given input SNR, as we increase beta, what will happen? More noise reduction. The noise reduction factor increases, which means that we suppress more noise. And the output SNR, the gain in SNR, will be also higher because we suppress more noise. Why, when we suppress more noise, the output SNR increases? You know why? Remember the maximum SNR filter? We talked in the time domain. Maximum SNR filter. When we suppress more noise, okay? When we suppress, we don't suppress noise in high SNR components. Where do we suppress the noise? In low SNR components, which means that we come closer and closer. The more components that we remove, we keep only the high SNR components until maybe we keep only the last component with the highest SNR. And then it becomes like the maximum SNR filter. Okay? That's why. So when we suppress more noise, the output SNR increases. If you did something wrong and you suppress more noise in the high SNR component, you remove the high SNR component, you also remove more noise. But this is not a smart thing to do, because then you increase the distortion and maybe the output SNR will not increase. Okay? So I connect you with things that we discussed. All things are connected. You see? When you understand these things. Okay, so because that we suppress noise in the lower in the lower SNR components, we necessarily, when we increase the noise reduction factor, we increase also the output SNR. But it comes at a cost of increasing the distortion. The distortion in weak speech components, not the strong speech components. Because we want, first, when we reduce noise, we want to reduce or suppress only the lowest in our components. So we have less distortion. But still we have distortion. So you see, when we increase the noise reduction factor, we also increase the desired signal reduction factor. So we have more distortion. We pay for that, okay? So when we have more noise reduction, more signal distortion. And the MSE, mean squared error, decreases. Okay? So beta and mu play here similar roles, which is nice to see. How the realization, so if we take a realization of noisy signal, so here the signal to noise ratio with this realization, I don't remember, I don't see that it's written, but probably realization. So probably it's in the code. I don't remember what is the signal to noise ratio here. Okay, but we have a certain signal to noise ratio here. And then this is the enhanced signal when beta equals to 1. So you see, when beta equals to 1, we still have many noise components where we don't have speech. Here, beta equals to 2. Here, beta equals to 3. So when we increase beta, we remove more noise. But you see, we also suppress or remove weak speech components. So we have more distortion. So what I want you to do is to take, read the code, the MATLAB code for this example, play with it. Play with it, change beta, listen to the reconstructed signal, play with ideal mask like this, play with ideal Wiener filter like this, which is combined with ideal mask, and some ideal mask with ideal ratio, and compare it to the non-ideal, something like that with beta. By the way, phi y, what do I do? How do I estimate phi y? Two ways. Either I can take phi y I can take it as magnitude squared. I can do that because these are the noisy measurements. So this is one way. But then try it. But in the code I didn't do this because there are variations because of the noise. So y is fluctuating. So instead of something like that, I took this and I took some averaging of neighboring time frequency beams. So when I compute for this time frequency beam, I take some window, like image smoothing. So this is the image, these are the samples. So I take some smoothing around it with a certain window. Let me see. Maybe it's before the sample. Here. You see, it's obtained two-dimensional convolution between the magnitude squared and a smoothing window. So I can take. So if I do more smoothing, then I distort the desired signal more. If I do less smoothing, then I have fluctuations. So this is also a trade-off. So you see, in practice, you have many trade-offs, many parameters. So you try something, you hear, you listen, you try to improve it. So play with it. And if you're interested to read a paper on speech enhancement, which you have some background on this, I can give you, I can recommend you. I can give you a paper. Just let me know. I will share it, okay, and then the WhatsApp group, okay? I can send it to you. For those who are interested, who have time. Any question? How do I estimate what? Which one? This, V? This? So this is what I said, that suppose that I have a voice activity detector here. You see? So suppose that I know when X is present and when it's not present. Voice activity detector, which is not easy, but there are some algorithms for voice activity detection. I can recursively estimate, average the noisy samples during inactivity of speech, and during activity of speech, I don't do any recursive averaging. So you need to work on that also. Because for speech, there are intervals where speech is not present, and if you have a voice activity detector, you can recursively estimate here. But if you have some applications that you know that the noise is stationary, and you know durations of periods that you have no signal, you see also with radar or something else, you know when there is a signal, when there is no signal, because you send the signal. But you need to know if the noise is stationary, because you calibrate or you make measurements during inactivity of the signal, so you assume that the variance remains the same when there is a signal, because I keep it. Yes, but the noise, maybe you have other interferences which are non-stationary. But if it's stationary, it's okay. So you estimate during inactivity. Mm-hmm. Yes. But if the variance of the noise it does not change, and you know that you didn't submit a signal, so you know some intervals where you don't have the desired signal, so you can get an estimate of the variance, which is okay, right? But I agree with you that there, in practice, you need to think what you do. You need to know what is the definition, when the signal, the noise, what is the type of noise, if it's stationary or not, if I can assume that the variance remain the same, how do I estimate it? I'll give you an example. Because you ask, so I have a good example. Suppose that there is a television somewhere here. And on the television it plays some speech and music and so on. And then I speak at the same time. So the speech, the desired signal, is non-stationary. But the noise from the television is also non-stationary. How do I suppress it? Okay? So it's more challenging. So also I can say, suppose that 5 people speak at the same time. 5 people speak at the same time, and I have a measurement, single channel measurement of 5 people. If I listen to it, it will be very difficult to listen to each one individually and to understand it. I need to concentrate, and maybe concentrate on the voice of one, and then another one, and then another. It will be, I can maybe, I can play something. Okay, I have a good example. I will play something, maybe after the break. I will look for a YouTube demonstration of something very nice. People speak at the same time. You see, it's difficult. And then I want to do source separation. Sometimes we call signal enhancement, where we have background noise and it's some sort of stationary. But source separation, 2 speech at the same time. two speakers speak at the same time, it's very difficult to listen. Not to mention if there are 5 speakers at the same time. Is it possible to separate, to extract just one of them? Any one of them. And then you can listen separately to each one of them. Very challenging. Is it possible? People are working on that. There are some solutions. Very nice. Very nice demo. I will show a demo after the break. Any other question? Because I don't want to waste time when I look for it. So I will do it during the break. Any other question? Okay. So until here, we worked with single channel signal enhancement. Now we want to move to multi-channel signal enhancement. How are we concerning the time? So we have, so it's 10:15. I'll give you like 5-10 minutes break, and then we start with multi-channel. Okay? Ah, okay, good.
And myself got 8.
Mm-hmm.
2 got 7. So remaining all around 3 to 7.
Okay, good. So it's good that we talked about the answers afterwards. Yes, so they understand. And they also Okay, so there are a few examples of source separation. One example is working in the time domain, single channel, or in the time frequency domain, but single channel, single microphone. Here I'm going to show you source separation of two speakers, but using audio-visual, which means that we use a single microphone and video to track the lips. But it's possible to do different things. Maybe the light here, maybe, or I don't know if people see it clearly. Okay. Maybe to dim the light. Okay, so I'll show you a few examples, like here. Note that, yes, this is good. Note that even though each one of them holds his own microphone, we don't use the signals in their microphones. Okay? So we don't use the signals that are received in their microphones. Then the problem is much easier to use these microphones. Even though each microphone receives the voice from here and also the voice from the interferer, but the signal-to-noise ratio using such a microphone is high. So it makes the problem easier. But we don't do that. Here we show an example of, we use just a camera, and we use the microphone and the camera. And then we want to separate both of them. So here, all is when you listen to both of them using the microphone and the camera, single microphone and the camera. Here, we can move it here, so we can listen to this guy. We move it to here, we can listen to this guy. Okay, so let's see this demo.
I'm not a fan of flying. I hate it. Hate being on planes. He might say, in general, there's so many noises. Solid. You know what I mean? I won't flush the toilet on an airplane because of the noise. Like, it scares me. You go, you hit flush, then you turn around, nothing happens for 5 seconds. Then out of nowhere, boom! Boom! Oh my God! I just put a hole in the plane.
The city bus does not terrify. It is like a little UN meeting on wheels every time you get on it. We all walk through the same door. We all pay the same price.
Okay, so let's remove this one. Let's see another example. Like this, cafeteria.
Okay, so the task is, given the video, any person who you see talking, their audio gets cleaned up, and everything else gets suppressed. Okay, so the task is, given the video, any person who you see talking, their audio gets cleaned up, and everything else gets suppressed.
Okay, let's see another example. Just a minute.
He's not on a Danny Ainge level, but he's above a Colangelo level. In other words, he understands enough to. If I
you said it was all right to lose on purpose. You said it's all right to lose on purpose.
Yeah, of course
and
it is. It's called
advertise that to the fans.
Who doesn't know that?
It's perfectly okay. Don't explain it away now. Don't explain it away. You said it was all right to lose on purpose. You said it's all right to lose on purpose and advertise that to the fans. It's perfectly okay.
He's not on a Danny Ainge level, but he's above a Colangelo level. In other words, he understands enough to. If I were a Sixers fan, yeah, of course it is. It's called tanking. Who doesn't know that?
Okay, so this. Okay, I don't know. Okay. You see in these examples that it's possible to separate, but it's not real time. It's offline. So it's recorded. So suppose that you see something, you record some video on your television or something like that, your camera, video camera, and you can process it in order to separate the sources. But it works offline using deep learning, audiovisual, and the complexity is quite high. But there are some methods that work even on single channel also. These kind of signals, even without the video, they work with deep learning because there are many parameters. It's much more difficult. So I encourage you to work on this example and try it, what we talked before. It will give you some insight. Any questions? By the way, here in the slides you have this paper, number 23. If you like, you can read it. And also on my website, in the journal publications, you have this paper and also a MATLAB code for speech enhancement. So you could try it. And actually it works in real time and also with signals. So you can play with it. You can listen to noisy recorded signals. Okay? Okay, so let's proceed. Now, after we talked about single channel in the time domain and single channel in the frequency domain, we move to multi-channel. So first we will talk about multi-channel in the time domain, then we will continue with multi-channel in the frequency domain. Okay, so if we have multi-channel, it means that we have more than a single sensor. We measure signals in multiple sensors. So we said that for single channel, we have the single channel model, and we will extend it to multi-channel model. So we will talk about the signal model, formulate the problem, then we will talk about some mathematical, which is called joint diagonalization, or something similar. Sometimes we call it generalized. Generalized eigenvectors and generalized eigenvalues. So a generalized eigenvalue decomposition. You know about the eigenvalue decomposition we talked about before. So generalized or joint diagonalization, it's also very useful. And we will talk about it. We'll talk about the linear filtering and performance measures and optimal filtering matrices. And I will explain why we talk about matrices, which is also some kind of a generalization of the single channel signal enhancement. But if you are already, know about single channel, you will see that the extension is much easier to multi-channel. So, okay. So let's start with the model. So instead of a single channel, now we have measurements. That each measurement, each signal that is measured in a sensor M, index M, is a combination of the desired signal, XM, plus noise signal in that sensor. Now we said that with a single channel, whatever is received here is the desired signal. But now we can assume that we have a desired source, and then we can take into account the reflections or the impulse response from the desired source to each of the sensors. Okay? Okay, so with a single channel, we assume that we have a measurement, yt, equals to xt plus vt. So here we assume that the desired signal is whatever is received due to the desired source in the single sensor. But usually, the source is somewhere in space. So here we have a source, desired source. And this sends wave, maybe acoustic wave, electromagnetic wave, whatever, propagating wave. This is the desired propagating wave. And this is measured by an array of sensors. So here we have Y1. We call it from 1, okay, 1, Y2, until we have Y, M, T. So we have M sensors. So here we don't need to assume that the desired signal is here. We can actually, each sensor received the source, the propagating wave from the desired source, convolution with impulse response, with a certain impulse response that takes into account all reflections from surfaces. And so it's not only delay, it can be impulse response that takes into account all the reflections from all surfaces, and then we receive the desired source component in the first sensor, in the second sensor, and so on. So each sensor receives the source, including the effect of reflections, plus the noise in that sensor. And the noise in that sensor, also, we can write it as convolution of some impulse responses from undesired sources, plus thermal noise, plus diffuse noise, plus any other type of noise. Okay? So this noise component is partially correlated between sensors. Here, the relation between sensor regarding the desired source is also given, something like that. Okay. So suppose that we know these impulse responses. It's a lot of information. If we know these impulse responses, it means that if we estimate, we can call this XMT. So this is the desired part of the speech that is, or the signal that is received in the sensor number N. So once we estimate any one of them, maybe X1T, or any one of them, if we know the impulse response from the source to that sensor, we can deconvolve. We can try to deconvolve and try to find XT. We can try to estimate XT from this set of measurements. And then we call it, to this task, we call it noise reduction or enhancement plus de-reverberation, because we try to estimate the signal from the source, the original signal from the source. So we call it de-reverberation or de-reverberated signal. So it includes both noise reduction and de-reverberation. But sometimes we say, okay, let's assume that one of the sensors that contains this impulse response is not the reflections are not that too significant. And it's mostly maybe a delay, like it's an impulse response with a delta, one impulse with a delay. Or maybe we don't care much about the reflections, about the reverberation. And in that case, we can choose one of the sensors, maybe the sensor with the least amount of reverberation. So this effect is the smallest. And try to estimate, let's call that sensor number 1. So we will estimate x1t out of this measurement. Okay? So we have two options. Either only signal enhancement, in this case, or signal enhancement and the reverberation, and we try to estimate the source from the noisy measurement, the noisy reverberant measurement. Okay? So in this lecture, I will concentrate on signal enhancement. But I want you to know that there are also problems that involve de-reverberation. I will not talk about it in this course, but those of you who are interested, I can give you something to read, a paper, so on, that try to do enhancement and de-reverberation at the same time. Some of you work on other tasks of signal enhancement. For example, image enhancement. So you are familiar with de-reverberation and noise reduction. You know that sometimes there is image reconstruction tasks. So you get an image, and the image is blurred. It's blurred because maybe there is a movement of the camera, or maybe a movement of the object while you're taking the image. So if the image is blurred, and you know the exact, what is called the impulse response in images, so it's point spread function, which is the impulse response. So if you know how the object is convolved, and then you get the blurred image, you can take the inverse, okay? So it's called deblurring for image, but it's the same, it's like de-reverberation. The problem is, deblurring, what will happen with deblurring? The noise will increase. So there are some trade-offs between noise reduction and deconvolution. If you try to do strict deconvolution, like this, if there is no noise, it's much easier. But if there is noise, direct inverse of deconvolution generates or increases the noise very sharply. As you are familiar, it's also similar that you know in mathematics. In mathematics, if you take the inverse of a singular matrix or a matrix with high condition number, which means that it's close to be singular, okay, even that it's not singular. So inverse of a matrix that with a high condition number, what will happen? Small error in the input. Small error in the input, what does it mean? Noise. Noisy measurement, small error in the input and the measurement will create high error, high noise at the output. Which means that after deconvolution, you increase the noise by a factor of the condition number. Okay? Those of you who understand what these terms, it's fine. If you don't, you can write these terms, look on the internet. What is condition number? What is the deblurring? How they done? If you're interested. If you're not interested, no problem. Okay? We continue with this, because I'm not going to talk about this, but if you're familiar, you see all these terms are connected in signal processing. Different applications, they call it slightly different. But They're all related. Okay, so we concentrate, we focus on signal enhancement, only signal enhancement. So we try to estimate or to find x1t, which means that we find x convolved with the impulse response from the source to one of the sensors that we choose. Which sensor will we choose? The one with the least amount of reverberation, obviously. So we will use the other signals in order to estimate this. Inverse transform, what do you mean? The impulse response? Here, I don't need it. I don't know the impulse response. I don't know G1t. I don't know. If I knew that, maybe I can estimate the source. But I don't estimate the source signal. I estimate the source signal as it received in one of the sensors. And we call the sensor that I choose, I call it reference sensor. Because I need, out of M sensors, I need to choose one of the sensor, and I call it the reference sensor. It means that this sensor, for me, if I didn't have noise, the signal that was measured in that sensor, maybe it has less reverberation, maybe it has higher signal-to-noise ratio. So I start with one of the sensors. You see, with the single sensor, the problem, I cannot choose a reference sensor because I have one. So I take this sensor, I try to suppress the noise. If I have multiple sensors, I can choose the best sensor or to choose arbitrarily. If I think all of them are the same quality, the signal or the SNR is the same, I will choose arbitrarily one of them. But if they are not the same, I will choose the best sensor, right? So if I choose the best sensor, already I improved the problem, I improved the performance compared to a single sensor, right? Already, by choosing the best sensor, already I did something. But now, not only that, I want to choose the best sensor. If I don't know which one the best sensor, just choose arbitrarily one of them. But suppose that I choose the best sensor, and then I want to use the other sensors to help me reduce the noise in that sensor. Okay? Understand the problem? So, instead of this, I have in the single channel, I will use only Y1. I will use only Y1 to estimate X1, right? For the single channel. In the multi-channel, I use all the measurements from 1 to M in order to estimate X1. So I have more information, more measurements. Okay? So how to do that? So what I do in the time domain, so this is the problem, okay? So now we understand the problem, and we also made some definitions. What is signal enhancement? What is joint signal enhancement and dereverberation or deblurring, whatever you call it? You understand the problem. So now, since we want to estimate only X1, we focus on signal enhancement, and we use all these signals. So what we can do in the time domain, we need to work on certain length of measurements. So what we do for each signal here, each sensor, we choose L samples, L past samples, and then we choose L past samples for each sensor, so we get ML samples Okay? So we have a vector y that instead of length L, just like in the single sensor, now it will contain ML samples, because we take L samples for each sensor and concatenate it into a long vector of ML sensors. Now, instead of estimating one sample at a time, you know, in the single channel, every time we estimated only one sample from the L samples of measurements. Now we can estimate maybe more than one sample, maybe 2 samples, 3 samples. Maybe we can estimate L samples, up to L samples. So actually we define Z, T, with line, whatever. Okay, so we will define. So this would be a vector of length either 1, 2, up to L samples. Okay, so just for the case of, because I don't want to carry all these values all over, I want you to understand, okay? So we worked with one sample also in the single channel. We can work with one sample at a time also for the multi-channel, and the methods will be similar to the single channel, right? Because if I want to estimate just one sample at a time from these ML samples, now that it's a vector of ML, I can work similarly to the single channel. But instead of working with vectors of length L, I will work with vectors of length ML. Will I get a better performance than single channel? Yes. Why? Because if I work with this correlation matrix, the correlation matrix, so it contains much more information. It contains not only correlations between 2 samples within the vector of length L. It contains the correlations between any sample within each vector of length L to any sample of even another vector of length L from another sensor. So all these correlations, they contain a lot of information. But similar to what we did with estimating a single sample from vector of L, we can change the filter. Now the filter, what will be the length of the filter? Okay, so it will be, the length will be a filter of length ML. And so in the single channel, we did something like that. We did H transpose YT. This was the linear filter that we tried to achieve. Remember? So it was like this. This was an estimate. So we can do it also here with the multi-channel. And then the same method that we worked in the single channel, we can do it here, but we will exploit information and correlation between channels. But I don't want to say something like that and then do it again with these vectors. Of course you can do that. But now I want to give you additional methods. So there is another way. Instead of estimating one sample, we can estimate up to L samples. So now, instead of this, I will write our estimate, which is x1 hat. So x1 will be a vector of x1t, x1t minus 1, and so on until x1t minus L plus 1. So it's a vector of length L. So I try to estimate a full vector from these ML measurements. Of course, in the single channel, it will not work. But in the multi-channels, because I have more than a single channel, I can do that. So, of course, if I estimate only one sample at a time, and the information is reliable, so the performance will be higher, but it's higher computational complexity. The more samples that I try to estimate from this vector, so I reduce the computational complexity because I estimate a whole block of samples from the same information. So the performance will degrade, but I also, the computational complexity will be lower because I don't need to repeat all these computations with the filters for each sample, but I estimate a block and then I estimate another block and so on. By the way, I can also do some overlap and add to average the blocks that I estimate. Also possible, just like with the inverse STFT. Okay, now let's try to simplify things. Okay, so suppose that I want to estimate this using a filter. So now the filter will be a matrix. I can call it H. And the size of H that I multiply with the vector T. Okay, just like this. So what will be the size of H? It will be L by ML, this matrix. You see, because the length of Y is ML samples, because it contains L samples from M sensors, and H is a vector, is an optimal filter of size L by ML, and then we get a block of L samples that we estimate that are related to the samples of the reference sensor. Okay? So maybe it's a lot of information for a short time, but you will see, you will understand all of this gradually. Okay? So even if I put maybe too much information in short time, but let's go through the mathematics and let's see, and you see that it's not that complicated. Okay. So here we have the measurements, and now we take, the first step is to take L samples for each sensor. So we have L noisy samples for each sensor, and then we concatenate them into a long vector of length ML. So YT is defined as taking the L samples from each sensor and concatenate them into a vector of length ML. And it's the same, defined for X and V, for the desired signal and the noise signal. So if in the single channel enhancement we assumed, in order to compute the variance of Rx and the variance of Rv, we assume that we know the correlation between any two samples of the desired signal and any two samples of the noise signal, as long as the length, the distance between the samples, is up to L samples. Now we need to know also the correlations between samples in different sensors. Okay? So it's more information, and if we use more reliable information, we will get better performance. If this more information is unreliable, it will be even worse than a single channel. Okay? So I told you, you need to remember in signal processing and also in life, if you use reliable information, you improve the performance. You improve whatever. If you go to somebody and you ask a question and you get unreliable answer, and you think that it's true, it's worse than not to get this unreliable answer. That's why when you use information, make sure that the information is correct. So if you have more information, covariance matrix or correlation matrix of Y, it's a longer vector. It contains more information. So this matrix, the correlation matrix, is ML by ML. So if you estimate something with more information and it contains wrong values, you will get worse result. Okay, so multi-channel signal enhancement is not necessarily better than single channel if you use information or you make estimation of this correlation matrix that is inaccurate. It's more sensitive. Okay? So, okay. It's more sensitive to false information. But suppose here life is much easier. In this course, we assume that we know this more information reliably, accurately. So here we use the correlation matrix of the vector Y, which is a matrix of ML by ML, large matrix. And we assume that we know each one individually, the correlation matrix of the desired signal and the correlation of the noise. And we assume that the rank of the noise, rank of RV, is ML, so it's full rank matrix. And the rank of Rx is smaller, is P, which is smaller than ML. Okay, so you remember that when the rank of Rx is smaller than full rank, we are able to reduce noise even without distorting the signal. This is important, just like MVDR. So we can reduce noise, we can minimize the noise under constraint of distortionless response, which is nice. That's why this is important, that the rank of Rx is smaller than ML, is not full rank. Otherwise, if it's full rank, still we can reduce noise, but necessarily it will come with signal distortion, which is still okay, because we can use Wiener or we can reduce noise from the weak signal components. And gradually, we will reduce noise from higher and higher, stronger signal components, and we get a good trade-off between noise reduction and signal distortion. But always we will have some trade-off. Okay. Let's continue. Joint diagonalization. So how do we find optimal criteria or performance measures and the optimal filter, which now it's a matrix, it's not a vector. In the single channel it was a vector, but now, because we want to estimate more than a single sample, so it becomes matrix filter. How do we find it? So we need to define performance measures and derivations. I sent you yesterday 2 files. One is about derivation of scalar functions and even non-scalar functions. How to do gradients with respect to a vector, and how to do derivations of formulas or expression, mathematical expression, with respect to matrices. Okay? So if you didn't have time to read it yesterday, I suggest that you read it and follow it, because it's important information. You will use it in signal processing and also in machine learning. And also I sent you another file, okay, which is also useful. So please go and read it, because it will be relevant to other topics that you study. Okay, so another useful way to reformulate the problem is to diagonalize these two matrices. It's just like what we did in the single channel. In the single channel, we diagonalize, we used eigenvalue decomposition of Rx. Here we take the Rx and Rv, these two matrices, and because they are symmetric, we can find the matrix T such that both become diagonal. So it diagonalizes two matrices. So if we have two symmetric matrices, one of them is full rank, then we can find a matrix T such that it diagonalizes Rv, which is the full rank, and we get here identity matrix, and it also diagonalizes the other matrix, with a symmetric matrix, and we get here diagonal matrix, but some of the values here will be 0. So we can order them in a decreasing order. Okay? So this is called either joint diagonalization or generalized eigenvalue decomposition. Take a look about the properties, open MATLAB. In MATLAB you have GEIG, generalized eigenvalue decomposition. And it's very useful because it makes things much easier. Okay, and the eigenvectors and eigenvalues are the eigenvectors are the columns in the matrix T, and the eigenvalues. So it's actually the eigenvectors of the matrix Rv minus 1 Rx with some normalization. Okay. Note that if we just diagonalize a certain matrix, we know that that the eigenvalue decomposition, the eigenvectors, are normalized. So the inner product between them, it's 0. But here, it's a full rank. So it's not the same. So there are other properties. So I just want to note that. Okay? So pay attention to that. So it's not a similar properties to diagonalizing a single matrix. And we have properties like this, that if we diagonalize the matrix Rx and Rv, so of course the matrix T also diagonalizes the correlation matrix of the measurements. So we get that. And we also know that this eigenvector, the inner product between the eigenvectors and the signal, any signal, so it's strictly 0 for the eigenvectors with the eigenvalues which are 0, just like what we had with the single channel. You see, so because the first P components of the eigenvectors in the matrix T, they span the signal subspace. So any inner product from P plus 1 to ML, this has to be 0 because the signal is not contained there. Which means that if we, just like what we did with the MVDR, derivation of the MVDR filter. So if we have measurements and we project the measurements into this subspace of the first P eigenvectors, and we don't touch them, and we remove the noise that is present in the noise only space, which is the space that is spanned from with the P plus 1 to the ML eigenvectors, we can remove noise without any distortion. So actually from here you see that we can achieve MVDR filter quite easily. We will work on the mathematical derivation, but you understand it because it's similar to what we did with MVDR in the single channel. Now, if we work on the first eigenvectors and we suppress them based on the signal to noise ratio and so on, so we can derive Wiener and other methods of filtering. Any questions? Okay. So then we will define linear filtering just like we defined, and then we will continue. But you deserve a tea break, right? I don't want to keep you from the tea break. So let's have 10 minutes break and continue, okay? We continue with linear filtering, performance measures, and how to find optimal matrix filters based on the performance measures. Okay? So we define the problem of signal enhancement using multiple sensors with, by applying the filter here, the filter matrix here. But if we work in the joint diagonalization domain, just like we do sometimes, we work in the Fourier transform domain, or we work in the STFT domain. So it's very useful to work in the joint diagonalization domain. So we compute the basis functions from the general eigenvalue decomposition, and then we transform the signals or the problem, both the problems and the filter to that domain. And over there, it's much easier. Why is it easier to work? Why is it easier to work in the transform domain instead of in the original time domain? Why? I repeat, remember we started in the time domain, then we work in the frequency domain. Why we move to the frequency domain? Because maybe in the frequency domain it's easier to separate the signals and the signal subspace, the signals from the noise. So if we are able to separate, to know where is the signal and where is the noise only subspace, it's much easier to find the MVDR, it's much easier to find more accurately the MVDR filter and so on. So we know that there are relations between the filters. So that's why we work also here. So instead of finding the matrix here, the matrix filter in the time domain, we will work in the transform domain. And which transform do we choose? The transform of the generalized eigenvalue decomposition, which I repeat, it's here. You see this matrix. This matrix enables us to separate between the signal subspace and the noise subspace. And then it's much easier to work over there. But in fact, to find this matrix, it requires some computational complexity, and if it's non-stationary signal, then this matrix or this transform changes over time, and sometimes we don't want to work with such complicated transforms, so we simplify it when we work in the Fourier transform domain or some fixed transform. But generally, if we know to separate the signals from the noise, the signal plus noise subspace from the noise only subspace, we know how to separate them, it's better to do it with that transform, as long as we can tolerate the computational complexity. Okay? So instead of working here with linear filtering, we can work in the transform domain. So you see this is in the time domain, multi-channel. So we have X filter desired simply by multiplying the signal X, this vector which contains ML samples, with the matrix, and also the noise with this matrix. This is the filtering matrix. We can work in the transform domain. So we can write H as A multiplied with T transpose. This means that instead of finding the matrix H in the time spatial-temporal domain, sometimes we call it spatial-temporal domain, because it contains sensors in the spatial domain and also samples in the time domain. So working with vectors of size ML like this, we call it enhancement in the spatial-temporal domain. Okay? So instead of working in the spatial-temporal domain with a filtering matrix, we transform everything to the signal using this matrix, T. And I remind you, this matrix T, the columns of the matrix T, are the generalized eigenvectors. And the generalized eigenvectors depend on the correlation matrix Rx and Rv, because it diagonalizes these matrices. That's why we call it the generalized eigenvalue decomposition. So if we know these matrices, which contains a lot of information, and in practice, it's very difficult to know these matrices. Okay? Sometimes, suppose that we know, we will see some examples that we know. And then we can find this like perfect transform that enables us to separate the signal plus noise subspace from the noise subspace, which is very good. And then instead of deriving the matrix H, we can derive the matrix A and simply multiply it with T transform. Okay, let's continue. So now we will, in order to find the optimal A, the matrix A is the filtering matrix in the transform domain. In order to find the optimal filtering matrix A in the transform domain, we need to define performance measures in the transform domain. And then find the derivative with respect to this filtering matrix and equate it to 0. This is the way. This is the mathematics behind optimization. Okay? So after we learned the single channel, so we are familiar with the mathematical foundations, with mathematical basics, how to do these things. So here it's slightly more complicated because we work with matrices instead of vectors, and we work with additional things. But so maybe the mathematics is a little bit more complicated. That's why it's important to understand the simple things first. But the understanding, the reasoning and understanding, it's the same, okay? Let's continue. So I remind you, we need to find performance measures as a function of the filtering matrix A. So the correlation matrix of the vector Z, we can write it as summation of the correlation matrix of the filter desired. This is the output, the estimate of the filtering after noise reduction. So we have the filtering matrix of the filter desired and the correlation matrix of the residual noise. So you see we can write it explicitly as a function of the matrix filter A, and this contains the eigenvalues, okay? The eigenvalues, the generalized eigenvalues, which we assume that we know. Why we know? Because if we know Rx and Rv, these are ML by ML matrices, long matrices. If we know this information, then we know the generalized eigenvectors, the columns in this matrix. So we know this matrix, the generalized eigenvectors, and we know the generalized eigenvalues. If we know this, we can compute this. So we assume along these derivations that we know Rx, Rv, we know T, so therefore we know T, we can compute T, and we can compute lambda. When we reach the next assignment, so I will give you assignment based on the multi-channel, you will see how to compute T and lambda from these matrices in the example. So you can follow the MATLAB code, how to implement this. Okay, but that's why I want you to understand. And then the derivations in practice by MATLAB code, I will give you so you can follow the steps, how to do it. Okay? First, I want to formulate the problem in the transform domain and to formulate the performance measures in the transform domain. Okay? Performance measures. So the input SNR, in the spatio-temporal domain, it looks like this. You see? Trace of Rx1 divided by trace of Rv1, which is the input SNR in the reference sensor. This is the input SNR because we would like to see, remember we talked about overview of multi-channel signal processing. We talked about array gain. Can somebody remind me what is array gain? What is array gain? Okay, so improvement of the signal to noise ratio at the output of what we measure, at the output of the array processing compared to the input SNR in the single channel, in the reference sensor, Okay? So this is the array gain. So here, this is the input SNR in the reference sensor, which we denote it as sensor number 1. And this is the output SNR, which is the signal to noise ratio at the output after the matrix filtering, which is the trace of Rx filter desired divided by trace of the noise, residual noise. And we can formulate this output SNR based on the matrix filtering, the filtering matrix, A, and things that we know, lambda, for example. Okay? And here we know Rx1 and Rv1, we know them. So if we want to find A, we want to find filtering matrix A such that it will maximize the output SNR, what do we need to do? To take the output SNR, this expression, to find derivative of this expression with regard to A. The only thing we don't know here is A. So if we find the derivative with regard to A and equate it to 0, we will find 8 that maximizes the output SNR. Okay? That's why when we optimize sync, we want to define things, formulate it as a function of A, and everything else we know. We know. We assume that we know. If we don't know, we need to estimate it. Okay. So RZ looks like that. This was before, and this, I think it went down. Okay, so we know that the output SNR is smaller than the lambda 1. Lambda 1 is the largest generalized eigenvalue. So it's the first component in the diagonal here. This is lambda 1. Let's define the noise reduction factor. Noise reduction factor is the trace, is how much noise was in the reference sensor. This is the reference sensor. So the trace of RV1 compared to the noise at the output of the filtering matrix, which is the trace of AA transpose. This is the noise reduction. And we want the noise reduction factor to be as large as possible. We can similarly define the desired signal reduction factor, which is what is the trace of Rx1, this is the desired signal in the reference sensor, divided by the power of the filter desired signal, which is the trace of A lambda A transpose. And we get similar expression that the gain in SNR for a matrix filtering A is the ratio between the noise reduction factor and the desired signal reduction factor. We can define the desired signal distortion index. So the desired signal distortion index is the expectation of the error between X filter desired, the desired signal which is estimated, which is given after the matrix filtering, compared to the block, to the vector of samples of the desired signal in the reference sensor. So you see, this vector is what we want to estimate. This is what we get at the output of the matrix filter, but it contains two parts. One is the filter desired and one is the residual noise. So for the distortion, we just look at the difference compared to the filter desired. Just like what we did with the single channel. And we normalize it. We normalize it with a trace of Rx1. So we get distortion. And yeah, the distortion is usually between 0. It's positive, you see? Positive. So it's between 0 and 1, and we want it to be as small as possible. We can define the mean squared error. So the mean squared error, we take into account the error between the output of the filtering matrix, Z, and the samples of the desired signal in the reference sensor. This is the error. And the error contains two components. One component is related to the distortion. The other component is related to the residual noise. And if we take the mean squared error of this, so it contains two components because the noise and the desired signal are uncorrelated. So we get that the mean squared error can be written as two components. One component is related to the MSE-based distortion. The other component is related to the MSE-based residual noise. So we want to minimize both. We want to get as small as possible distortion, and as small as possible residual noise. But of course, we cannot, if we try to minimize one, the other one will increase. If we try to minimize the noise, the distortion will increase. One comes at the cost of the other. So the MSE, we try to minimize their summation, their sum. And then we get the Wiener filtering matrix. And if we add here a factor mu, here, what do we get? Trade-off. Exactly. So if we add here mu, we get a trade-off between noise reduction and distortion. If mu is larger than 1, the trade-off filtering matrix will try to reduce more noise, but will get higher distortion. If mu is smaller than 1, it will suppress less noise and will get less distortion. Okay, so this parameter, so we'll see that, you see, even here, when you formulate the problem, already we understand 3 different types of filtering matrices. One filtering matrix is MVDR, which is simple. In the transform domain, we keep the projection in the first P eigenvectors. If we keep these components from the measurement y, we take the measurement y, this vector, and we keep the components in the signal subspace that is spanned by the first P eigenvectors. We suppress the noise-only subspace, we get in MVDR. If we take the mean squared error, we try to minimize it, we get the Wiener filtering matrix. If we put here mu, we get the trade-off filtering matrix, and so on. So you see the similarity between what we learned already and how we work with the multi-channel. Okay, but there are some things beyond that, okay? But there are some similarities. I will stress things which are different also. How do we find the Wiener filtering matrix? Okay, so you think, okay, what do we have? We have here an expression, mathematical expression. When you want to find optimal of a function, so you need to write the function that you want to minimize or maximize explicitly as the variable. Here the variable is A, the filtering matrix, and everything else is known. You see here, everything is known. And also, only what is missing is the matrix A. And then you need to find the gradient of JA, the mean squared error as a function of A, with respect to the matrix A. And now you try to find this derivative, but you see trace, you see matrices, and maybe you are not familiar with that, which is fine if you're not familiar with that. That's why I sent you yesterday, some material, how to do derivative of this. And even if you don't have the material I gave you, you can find information on the internet how to do these derivatives. Okay? And it's useful because it helps, just like you study integrals and derivatives and so on. So this kind of formula are very useful. Okay, but it's not difficult to estimate or to find the derivative. And we will see how to do that. Okay. Maybe it's a good to include this. So when we get the Wiener filtering matrix, so see from the material I gave you or from formula on the internet how to find the derivative of this expression. Okay? So it's a good exercise. Okay, so we have some relations between the MSC, the ratio, just like we had a single channel. Don't want to go beyond that. Okay, now let's talk about the Wiener filtering matrix. So we need to find the minimization of JA, just like I said. And then the solution is this one. Okay? So try to prove that this is the solution, but not from, don't put the solution in the derivative over there, but try to find the derivative. It's a good exercise, especially if you're not familiar how to do the derivatives or gradients of scalar functions as a function of a matrix. Okay? So it's a good practice. Now we find, so we can write the Wiener filtering matrix this way, because we defined it. This is the Wiener filtering matrix in the transform domain. Now, if we want to have it in the spatio-temporal domain, we need to multiply it from the right with the matrix T transpose. So if we open this, we see that we can write it this way. Okay, so let's write it here. So we can write it as the Wiener filtering matrix. We can write it as matrix I, which is defined as identity matrix and all zeros. Okay, so it's defined. Rx, summation from I equals to 1 to ML, Ti transpose. These are the eigenvectors, generalized eigenvectors, so the columns in the matrix T. 1 plus lambda I. Very nice. This is a Wiener filter. Wiener filtering matrix. And what we have here, of course we can express the Wiener filtering matrix like this, but I will show you why it is useful over there to write it like that. And then we also see that the Wiener filtering matrix, just like with the single channel, it always improves, or at least does not degrade, is that always you get some gain in SNR. Larger or equal to 0. So the output SNR will be not smaller than the input SNR. The more information that we get, the higher signal-to-noise ratio that we get at the output. Let's see an example. Okay, so the assignment today will be to repeat this example. Or maybe I'll give you another one. Okay, but let's understand this problem. So suppose that we have a source signal that comes from a certain direction, and then we have M sensors, uniform linear array, which means that all sensors are on a line, and the distances between the sensors is fixed, is D. And we know the configuration of the array. We know the sensors' placements exactly, okay? Suppose that the desired signal, the desired source, transmits a wave, far field, okay? Far field wave that looks like this. A cosine 2 pi f0 t plus phi. A is not known, but A is constant. F0 is the frequency, and phi is random phase uniformly distributed between 0 and 2 pi. And we have additional Gaussian noise. But now, because we have multi-channel, and also we have some thermal noise, but because we work with multiple sensors, we need to know also where the wave, or the source signal and the interference, where they come from. So we assume that the desired source is from the broadside, theta equals to 90 degrees, and interference is from the end fire direction. It's from 0 degrees. And in addition, we have some level of thermal noise. Okay? So we can write this example that each sensor receives a desired signal plus noise. And the noise is a superposition of interference plus thermal noise. So based on this example, we see that the desired signal, because it comes from the broadside, so if we have an array like this, and the desired source comes from 90 degrees, from here. So all the desired signals in all the sensors are the same. Okay? So xi is the signal, the desired signal that is received in sensor number I. So it's the same as the desired signal that is received in the reference sensor. All the same. But for the interference, it's not the same, because the interference, U, it comes from this direction, from the end fire. Theta equals to 0. So if the interference comes from here, so the correlation between samples depends on the delay, how long it takes to propagate from one sensor to another. So you see, this is the relation of a sample T compared to the sample T minus tau in the reference sensor. This is the reference sensor number 1. So if we take sensor number I, so the sensor number I, so sample T is like the sample T minus tau I that was at the first sensor. And this is the time that it takes to propagate from the first sensor to sensor number I. So it's just delay, because it propagates from this direction. Okay? Give you a simple example, just so you understand. So using this information, that we know the direction and so on, we can find these matrices, Rx and Rv. Okay? So how does it look? So I can construct these matrices according to the relations between the signals. So Rx will be Rx1, Kronecker product with a matrix of all ones, because the same signals are received. So I don't want to waste too much time on the derivation. You get it in the assignment. Okay, so you can follow one by one equation and make sure that everything is correct. And also we can find this matrix, Ru, for the interference. And for the thermal noise, what do you think? The thermal noise, what will it be? The matrix, correlation matrix. For the thermal noise, it's totally uncorrelated, because any sample from one sensor is uncorrelated with any sample from another sensor. So it's a diagonal, and if it's the same level of noise, thermal noise, so it's sigma squared of some level, sigma W squared, multiplied with a diagonal matrix, identity matrix. Okay? So here we know all this. You see here, this is the thermal noise, the contribution of the thermal noise. This is the interference. And together we have the correlation matrix of the noise. And then we can compute from this two matrices. We can compute the generalized eigenvectors and the generalized eigenvalues and sort the eigenvalues according in a decreasing order. Okay? We can also compute the input SNR for this specific example. And let's see an example, or specific example with these values. Suppose that A equals to half, F0 is 0.1, the variance of the interference is 0.5, the variance of the thermal noise is 1% compared to interference. So it's low thermal noise. Why do I choose for this example low thermal noise? Because you see, when I use multi-channel sensor array, it works best to reduce noise that comes from a certain direction, directional noise. If the noise is thermal, I still can reduce it by averaging the signals. For example, if I have only thermal noise and the source comes from this direction, so the source comes to all sensors from this direction, so there is no delay. So I can just average these signals. What will I get? Higher SNR. So I can reduce the thermal noise by averaging the signals. But if I have an interference, I can suppress it much better than just averaging. I can suppress it such that I will get some kind of null in that direction, in the beam pattern. We talked about the beam pattern. So I want to reduce beam patterns, so a signal that comes from this direction will be suppressed as much as possible based on the direction. So the filtering matrix takes into account the correlation between samples here and samples in any of the sensors. And based on these correlations, try to minimize the amount of signal that is measured from this direction. Okay? This is what we're trying to do. Okay, so let's see how the Wiener filtering matrix, how it performs as a function of L and the number of sensors. So here we have the gain in SNR, and here we have the minimum mean squared error, which is the MSC by using the Wiener filtering matrix. And as a function of L, and each color corresponds to a different number of sensors, different number M. So the blue is for M equals to 1, which is a single channel. M equals to 2, this is the green, 2 sensors. Here is 5 sensors, and here it's 10 sensors. So what we can observe, that when we increase L, the number of samples that we use for each sensor, or when we increase M, the number of sensors for fixed L, we increase the number of sensors, we get improved output SNR. We improve the gain in SNR. Very nice. But this is obvious. Even if I ask you, without showing you this example, you would agree, right? When you increase L, or when you increase M, you increase the number of sensors, you increase the samples, you have a longer vector here, because you use more samples from each sensor and you have more sensors, so you use a longer signal, longer vector of measurements. So you use more measurements, so you can estimate better the desired signal. Of course, makes sense. But my question is, what do you think for this specific example? What is more important? To take more temporal samples or to take more sensors? what is more important. Okay? So suppose that this vector, the size of this vector is 20. 20. But I don't tell you what is M and what is L. The size. So the complexity of working with something like that is the same. Okay? Size, length, M, the matrices, and so on. Okay. So I can choose 20 samples, L equals to 20, and choose one sensor. So the gain in SNR will be something like that, less than 10 dB. Okay? Or maybe I can take 10 samples, L equals to 10, and 2 sensors. Wow, this is a big jump. The gain in SNR increased to 20 dB. So I can reduce L and increase the number of sensors. So the effect of increasing the number of sensors is much more than taking more samples from each sensor. So increasing L is much more important than increasing L. We want to use more sensors. This is one observation. Another observation, we see that when we take 2 sensors compared to 1 sensor, there is a big jump in the output SNR. But when we increase from 2 to 5, it's less. The jump is less than jump from 1 to 2. Which means, what does it mean? That the significance of additional sensors decreases. The more sensors that we have, the additional of one more sensor is less significant. So the big jump comes when we increase from 1 to 2. Because with 1, we don't have any spatial information. With 2 sensors, already we add some spatial information. So we can separate between source that comes from certain direction and source that comes from another direction. We have this spatial information. Now, if we add more sensors, the significance of the additional sensor becomes less and less. So here is the jump from 5 sensors to 10 sensors. See? So it decreases. And of course, the MSE decreases, the mean squared error divided by L. Why do we divide the MSE by L? Because we want the average MSE relative to a single sample. Because remember that we estimate a block of L samples. So the MSE that we wrote before is the MSE, the total MSE over all the L samples. So if we want the average MSE per sample, we need to divide it by L. Okay? So we see that the average MSE for each sample reduces when we increase L or when we increase the number of sensors. This is beautiful. But this information, it's a lot. And we assume that we know this information. If this information is incorrect, we will not get these nice plots if the information is incorrect. But it's correct because it's based on the simulated signals. We simulated signal and we computed these matrices from the simulated signals. Okay? That's why we have it. Now, suppose that we choose L equals to 30, and we change the variance of the interference such that we change it from the input SNR from minus 5 dB to 15 dB. Okay? So we plot the gain in SNR, the MSE, the noise reduction factor, the desired signal reduction factor as a function of the input SNR for different number of sensors. The blue is 1 sensor. This is 2 sensors, 5 sensors, and 10 sensors. Okay, so you see, the more sensors that we use, we're able to reduce more noise. makes sense. Why? Because we use more information. If we add more sensors, you see, what is the information that we use? We use, in these matrices, we use the information which is a correlation for any sample in the reference sensor, or actually between any sample in the vector of L samples in one sensor compared to any sample in another sensor within the vector of L samples. So the more information that we use, we add sensors, so we need more information, we use more information, therefore we improve the noise reduction and the output SNR. Regarding the MSC, we are able to reduce the MSC. Regarding the distortion, you see there is a big jump in the distortion, reduction of the distortion, when we jump from one sensor to more than one sensor, 2 or more. You see, there is a big jump. Why? Okay? Why is that? Why the jump is here? You see, because for this example, when we have the desired source, if we have one sensor, in order to reduce noise, we use the filtering, the Wiener filtering matrix. So in order to reduce noise, we need to distort the signal. But even if we have we have two sensors, we can reduce interference. Here the interference is the dominating noise. The thermal noise is relatively low. So even with 2 sensors, we can reduce much of the interference based on its direction without distorting much of the desired signal. So we can actually, what we get is just like some sort of a null to that direction. We can suppress much of the interference even with 2 sensors. And of course, the more sensors that we use, we can suppress even more noise. But the distortion will be small. Okay, so we don't sacrifice much of the distortion into the noise reduction. Here it will be smaller because we use spatial information, and the interference and noise and desired signal come from different directions. Mike, a question. Suppose that the interference comes from 90 degrees. Both desired signal, interference, both come from 90 degrees. What do you think? If we add more sensors, do we get better performance? No. It doesn't add any information. Because there is no spatial separation. They come from the same direction. And here it's without any reflections. Okay, if there are different reflections patterns, different impulse response, something else. Okay? But if both are in the far field and come from the same direction, the fact that we use more than one sensor, it's not going to help because we don't have spatial separation. If one is close and one is far, so it's one in near field, one is far field, it's okay. We can add. And then we can use multiple sensors. But if both far field from the same direction, we cannot suppress noise from that direction without sacrifice of the distortion of the desired signal. This is a realization of this example. So this is the noisy signal. The noisy signal is with -5 dB realization. This is an estimate of the desired signal using a single sensor, m equals to 1. This is with m equals to 2 sensors. You see the big improvement, even 2 sensors. This is obtained with 5 sensors. Very nice. Using the Wiener filtering matrix. And I didn't use the fact that it's, I didn't try to estimate A and F0, the amplitude of the signal and the frequency and the phase. I only applied the Wiener filtering matrix, but I used this information of A, F0, and the phase. The phase is random, so I don't need it. But I used A and F0 for obtaining Rx in this information. And I also used the direction of an arrival, so I know where it comes from. I use it for Rx, and I use the direction here for RV. Okay, so the assignment is to go carefully, it's very important, to go carefully through this example, these figures, 1 to 5, or what we have, 2 to 5? Here, 3. 3, 4, 5, these figures. So follow these figures and the MATLAB code and try to understand. Any question? Play with it. It's important. Okay. Now, because I have this expression, which is a very nice expression for the Wiener filtering matrix, because it's based on some summation. So when I get such an expression, I can ask myself, what if instead of this summation, over all the generalized eigenvectors from 1 to ml, I will take less in the summation, from I to Q, something like this. And Q is between 1 and ml. Okay, so if Q in the summation is ml, we get the Wiener filtering matrix. But what happens if I reduce Q? Q will be smaller. What do you think? What will happen? If I reduce Q, do I reduce more noise or less noise? If I take Q smaller, what happens? More noise, exactly. So here I process or I filter all the components in the transform domain, in the generalized transform domain, or joint diagonalization. If here I take smaller summation, only Q in the summation, it means that I take some components and I remove them. Okay, so I suppress them, I put them 0. So H, those components will be 0. So by taking smaller Q, if Q goes down, smaller Q, we're able to increase the noise reduction. But then we pay for that. If we increase noise reduction, we get increased distortion. This is the trade-off. But at least it enables us to find some filters with trade-offs. Okay? So it's possible also to put mu. Remember mu in the... But it's also possible to take this some alternative. So we find other expressions or other filters that enable us to be more flexible with the trade-offs between reduction and distortion. Okay, so it's a nice way. So if we take only one component, the first component, you see Q equals to 1, actually we keep only the one with the highest signal-to-noise ratio. So this filtering matrix will maximize the output signal-to-noise ratio. But this is one form. We will see that we have other forms. Remember that with the maximum SNR filtering, just like the single channel, we have an additional degree of freedom. Over there we had a variable zeta. So also here we have additional degree of freedom. So this, we have actually many possible ways to get filtering matrices that maximize the SNR. So this, if we take Q equals to 1, is one of the solutions, because we see the output SNR is the maximum possible. And, but this is the, this one is the maximum SNR filtering matrix with minimum MSE. Why? Because we obtained it with the Wiener filtering matrix. And then we take the Wiener filtering matrix, and we take only the first component. So it's both the maximum SNR and the free parameter, just like in the single channel, is the one that obtains minimum MSE. So if you take all possible solutions of maximum SNR filtering matrix, and you want to find the free variable such that the MSE is minimum, you will get this solution. So I can define this problem, and you need to find the solution. And actually, this is what you get. But we also get it directly from here. Okay? So this is another, a nice way. So this is the same or different example. Okay, different example. You can follow also this example. Suppose that we have X that goes like, the correlation goes like this. We have an interference from a certain direction. We have additional thermal noise and so on. So this will be the example. But what I want to show is the effect of changing the value of Q. You see? So this is the gain in SNR, the MSE, the noise reduction factor, and the desired signal reduction factor. So here, this is the blue line for Q as a function of input SNR. The blue line is for Q equals to 1. So you see, for Q equals to 1, the gain in SNR is maximal. The green is for Q equals to 2. And then the red is for Q equals to 5. And this cyan color is for Q equals to 9. So you see, when you increase Q, you decrease less noise, because you increase the dimension of the signal that you keep. So you decrease less noise. So the noise reduction factor decreases. And also the output SNR decreases. But then, when you decrease less noise, you also get less distortion. And vice versa. If you take Q equals to 1, this is the maximum noise reduction. And then the SNR will be maximal, but the MSE will be maximal, and the distortion will be maximal. Any questions? If one element what? If one sensor doesn't work, so it means that if you choose the reference sensor as the sensor that doesn't work, then you will not get anything. It will be problematic. But if one of the sensors here doesn't work, but you choose the reference sensor, and one of the sensors here doesn't give you any information, then the correlation, in the correlation matrix, you don't have any correlation. So it will not be used. This information is just like taking another sensor, and there is no correlation to the desired signal and no correlation to the noise. So it doesn't affect. It's just like removing. Okay? It's just like taking another sensor. Suppose that I have desired source, interference, and one of the sensors is beyond the wall. It doesn't get any one of them. Maybe it gets another noise that is unrelated to this one. So this sensor is not useful. So it will not contribute anything to the performance. Okay? But if you choose that sensor as the reference, then you are not able to estimate. I said choosing the reference sensor, you need to choose wisely. The best sensor, choose it as the reference. And then you try to use the other sensors to help you to improve what you can get beyond single channel. If you choose a bad sensor as the beginning, it's not good. You know? So it's important to choose the best sensor first, as much as you can. If you don't know, choose, you can compare them online and then choose and then to take. But it's important to choose the reference, of course. Any other question? Okay, so tomorrow we will continue. So we saw something very nice, okay? So go over these MATLAB codes and so on, and also what I gave you before with the speech enhancement. These are beautiful things. And follow the derivations. Tomorrow we will continue with MVDR, control distortion, we will see, and the trade-off. Also something that generalizes all this. So if something is not clear, follow these slides, understand it, and then it will be easy to follow the other derivations. Okay? And tomorrow we will move from the time domain to the frequency domain. So if you are not familiar yet, something you don't understand with single channel, it's important to understand that. You see, after we understand how to do in the single channel, generalization to multi-channel, it's much easier because we understand. When you work in signal processing, it's not like you try to solve something mathematically. It's not working in signal processing. Signal processing, you need to understand the physics behind the measurements, the model, how to combine, and all these derivations. So it's a combination of understanding and the mathematics behind it. Okay? That's why if something is not clear, it's important because tomorrow we will continue and we will extend the single channel in the frequency domain to the multi-channel, also in the frequency domain. Okay? Thank you. So we'll meet tomorrow. If you have other questions that you want to ask me, you can also ask me now.